So we're going to start with fitting the frequency models in R as our starting point. So do not be afraid to leave any comment or question in the chat. That's where the tool is for, right? So what's the idea? Throughout the course, we've been working with this frequency severity approach. And you know that a technical premium or a risk premium or a technical price, if you want, we can construct that by building a model for the expected claim frequency and multiplying it with our calibration of the expected claim severity. So that's why we typically build two models, one for frequency, one for severity. We typically make the assumption of independence between frequency, severity. And in this case, so in this particular session for today and for Thursday, we're going to ignore any available covariates. We'll come to that next year, right? So what you need to know for now is that each record I in our dataset registers the exposure. And in this case, it's the fraction of the year in which the contract was active. We've got the number of claims. So that's the observed claim count in the period of exposure. And we also have the average claim size, which is per reported claim. It's you can see it as the total losses observed in the period of exposure divided by the number of claims reported, so that you get a kind of average claim size. That's typically what we refer to as the severity. Yeah. So the first thing I want to start with is bringing you back to the AB0 class. So let's say that n is a count or a frequency random variable. It has a certain probability function denoted here with pk. So that's the probability that n is equal to k. And then we also remember that in the so-called AB0 class for frequency distributions, we need to be able to write the probability function using the recursive relation that you see here on the sheets. So you should be able to identify an A and a B such that this recursion holds. And we also remember that certain members of the class are very popular count distributions like the Poisson, like the negative binomial, right? So what I want to do now is I want to verify on the data that we stored in the object MTPL, what this AB0 recursion, what it would look like, and what kind of values we retrieve for the parameter A and for the parameter B. And this is just a recap. So here you see these three very popular AB0 class distributions being summarized. You see again that for example, the negative binomial distribution, we would have a slope A that is strictly positive. We've got the probability function, we've got the parameters, we've got the moments, and so on and so forth. Yeah. So what we're going to do now is we're going to go to the data and we're going to look a little bit at this relation. And of course, this is just one way of implementing this relation, but I'm going to calculate the empirical probabilities, and I'm going to calculate this, this expression k times pk divided by pk minus 1, right? And what I'm then going to do if I have this expression is that I'm going to fit a linear model to it, yeah? So I'm going to fit a linear model to it where I use as the covariate the k, and where I will be interested in getting the intercept B and getting the slope parameter A and seeing how this linear expression behaves on my data, seeing what the sign of this fitted slope A will be like, right? So that's what this code is doing. And of course, there are multiple ways of implementing this stuff, but what I did is I started from the MTPL, $n claims. So that means that I took the variable n claims in the dataset MTPL. I asked to create a table from there, and I asked to create a proportionality table, so prop table, and that gives me the empirical probabilities. So that will tell me empirically in my dataset which percentage of the observations resulted in 0 claims, in 1 claim, 2 claim, and so on. Yeah, so we're going to see right away in the cloud how that looks like. We're going to store these empirical probabilities as a numerical vector. and we're going to use them to create the following relation, right? So that's what's happening over here. So I'm going to work with the AB0 relation, and that will be my empirical probabilities to observe an outcome k, divided by the empirical probability to observe an outcome k minus 1, multiplied with k, right? So you have to be a little bit careful. The k runs here from 1 to the highest number of claims that I observed. And then, of course, you let the relation that you want to evaluate here, you let it start from k equal to 1. And we know that in R, vectors or the indexation of vectors start with a 1, right? So if I look at the empirical probability at position 1, then I'm looking at the empirical probability to observe an outcome 0. We'll see that right away in the code. So we store the things we calculated in a data set, in a tibble. So we're going to work now with this tibble AB0 data, and on this tibble, we're going to fit a linear model and picture the fit that we constructed as such. Yeah. So let's do that. Let's see how that goes. So we're going to go back to the cloud and see how that goes. So if you scroll down in the program we were working with, you will see here an indication that the frequency modeling should start, and you're going to try out the instructions that we have over here. So first of all, I look at the number of claims. I create a table. So if I would just do this instruction, mtpl $n claims, and then the pipe operator table, you'll see that you'll get a table going from 0 to 5, and then the number of times we observed outcome 0, outcome 1, outcome 2 in our data set. If we do add the instruction prop table, then we'll get a proportionality table, and you'll get the same information, but now expressed with percentages. And of course, this is a little bit awkward to work with, so I really want to have this information as a numerical vector. And that means if I do the following instruction, then in the object empirical, I now have the percentages that I'm going to work with. Yeah. So that helps me to put together the vector k. So how is my k going to run? So if I go with k from 1 to 5, right? Then I want to put this AB0 relation together, like we said. So we're going to start with the empirical on position 1. So empirical on position 1, that's the empirical probability to get an outcome 0. The empirical on position 2, that's the empirical probability to get an outcome 1. And I'm going to multiply that with k equal to 1. So that's how I programmed this AB0 relation. So if I do AB0 relation, you should see the ratios coming up. Then I put the whole thing together in a small data set, which is called AB0 data. So here you see the k, you see the relation that comes with this k. And then I'm going to do this ggplot where I say, okay, let's create, I already had the data frame, so I didn't need to create this instruction here. That's a bit redundant. But what I could do then is I could put on the x-axis the k values, on the y-axis the relation that I calculated. Black and white theme, I add points and I add a smooth line where I'm asking to add the fit from this linear model. Yeah. So to make it a bit more concise, I could rewrite. I could rewrite my instructions by relying on the data set which I created higher up. So that was the AB0 data. And I can put on the x-axis the k's. And if I look at the structure of my AB0 data set, I've got for the y values AB0 this. Right. So this instruction should hopefully also work, should give me exactly the same kind of thing. Yeah, so that's a little bit more relying on the instructions that I considered higher on. What about this linear model fit? So we can try to do the linear model fit explicitly, I guess. So there we could ask to do a linear model of the AB0 versus K on the data set AB0 data. And then if you look at this linear model, you will see what the intercept is going to be, and you will see what the fitted slope is going to be. That's going to be 0.12. So that is a positive slope that you fit here. So what we get as an indication from exploring this AB0 relation is that the negative binomial seems to be a good starting point to model this kind of data. And that's what you see also here in the plot. So you have this increasing slope, you've got a linear relation here. So these are all points that indicate us towards the use of the negative binomial as the frequency distribution here. Good. The empirical variance then also deserves your attention, and I think it's best explained on the sheets because there it's a bit more in detail. So for the empirical variance, I'm gonna sort of implement the relation that you see over here by again accounting for exposure. Yeah. So what we're gonna say is the X, that's the N claims in our data set. But this N claims is registered over a certain period of exposure. So if we compare the N claims with its expected value, then this expected value, it should be like the global average or the global the global empirical mean, but multiplied with the exposure for this particular observation, right? So that's what you see coded in the R script there. Then we take the squared difference and we're going to average all of these once again by taking the exposure into account. Yeah. So that's how I would implement this empirical variance, which I agree is not so straightforward, but that's what's going on over here. So we look at the number of claims registered on a policyholder. We compare that with what we would expect for this policyholder, taking into account his exposure and taking into account the global empirical mean. We take the square differences, we sum that, and we derive by the sum of the total exposure. And if we do that, we get an empirical variance of 15%, whereas the empirical mean is around 14%. So empirically, we see some over-dispersion in our data, and the variance is larger than the mean. Okay, so that being said, we're now ready to fit some of our models. So I'm going to show that first on the screen, on the sheets, and then we're going to go back to the coding part. So what we want to do now is we want to fit a distribution to the data set by maximizing a likelihood over the unknown parameter theta. So you see here again the idea of a likelihood. You see the idea of switching to the log likelihood. And numerically, what we often do is we switch to the negative log likelihood. And the reason for that is that in many tools like R, optimization routines are written by default for minimization, right? So if you want to use a minimization routine here, you should minimize the negative log likelihood. And be careful, if we include exposure, we typically want to bring that in the mean of our distribution. For example, if you do a Poisson, then you in fact want to calibrate the following model. So the NI is Poisson distributed with as the mean, the exposure multiplied with the expected annual claim frequency lambda, right? And the exposure is given, it's given in our data set. And the lambda, that's something that we need to calibrate, right? And we're going to do that by maximizing the likelihood, by maximizing the log likelihood, or by minimizing the negative log likelihood. So what are we going to do now? We're going to fit this kind of parametric count distributions to data, the data stored in the MTPL object, And we're going to do that with R. So there are a few options now that you have, and I'm going to walk you through a few of these options. So a first and rather naive solution would be to rely on a built-in function that is called fit_distrib. So fit a distribution, which is part of the mass library in R. So then the code is very simple, I would say. You just load this library mass, you call the function fit_distrib, and you say, okay, I want to fit this distribution to the following outcome, the number of claims, and which distribution do I want to do, the Poisson. So then the result for lambda and the standard error that comes with it is given as such. So my question to you is, do you recognize this number, and why is this solution not appealing to us? So you can try it yourself and you can reflect a little bit on it. So if I go back to my code, I could load the library mass, I could do fit_distrib, and I should see this fitted lambda for the Poisson distribution coming up. Very good. This is the mean in the classic meaning. This is the sample mean, number of claims divided by number of observations. So what this routine is ignoring is this exposure measure, right? So this is a very standard way, ignoring exposure, fitting a count distribution to my data. If you're interested in this function, you can always do like question mark fit_dist. Oops. And then we go to the help. We're here on the right-hand side. And here you get an overview of the kind of densities that are available here in this built-in routine, whenever you need that. Okay. Good, so that's a first naive approach. We're not going to do that because it ignores the exposure. And now I'm going to see two solutions that do work. And one is using the so-called GLM function. GLM is for generalized linear model in R. And this is a routine, or this is a framework that I'm extensively going to discuss in my data science course. But I want to show it to you here because it works, and I can easily apply this GLM function here to calibrate the model. Yeah. So first of all, once again, ignoring the exposure. And I'm going to say, okay, what I want to do is I want to calibrate a Poisson model to the number of claims here. That's my Y, that's my outcome variable. And the only thing I want to include here is a so-called intercept, so parameter beta 0. And I want to work with the Poisson distribution with, as the so-called link function, the logarithmic link function. So what this routine in fact is doing is it calibrates a Poisson with the following structure or the following specification for the mean. So it says that the logarithm of the mean of Y is an intercept. So that means that if you bring this log to the other side, it means that the expected value of Y is the exponential of an intercept is the lambda. So again, this ignores the exposure, but it allows me to verify if I take the exponential of the fitted intercept, I should get the same the same lambda as what I have over here. Yeah. So let's check how that works in R. So here is a first step. So I can do this frec GLM Poisson. I could inspect the results by typing the name of the object. And then I see the intercept that is calibrated is like minus 1.971, right? I could also, in a more clever way, ask for the results with this broom function. This is just a more tidy way to get the output from calibrating a regression model. And I see that, okay, I've got an estimate of minus 1.97. Yeah? So if I would take the exponential of this frec GLM Poisson and then the coefficient, then I get, here I did include the exposure already, sorry. So my code on the sheet was just a little bit simpler. So let me first ignore the exposure. Then I get the following results, right? And if I then take the exponential, I get the 0.12, which I also had before with my fit distribution, right? So this would be a continuation of the naive approach where you can work with instructions of the following form. Okay. However, what we now want to do is we want to include the exposure measure. So that's what I'm going to do on the next sheet, which I was actually already doing in the R code. And I'm going to extend this GLM instruction, and I'm going to include a so-called offset. And that offset is equal to the logarithm of the exposure. Now in statistics, what an offset is doing is it puts a term, an additional term in your so-called predictor. So that's in your regression structure. But for an offset, you're not going to calibrate a parameter beta, right? So what we do now is we sort of calibrate the following structure, and you see that here on the right-hand side. So we calibrate this specification for the logarithm of the expected value of y. So if we bring then the logarithm to the other side, what we're actually doing is we get the expected value of y as the exposure times the exponential of beta 0. So what we're doing now is we're actually coming up with the specification as I want it to be, and we explicitly account for the exposure in my structure for the mean. Okay, and if you now look at the resulting estimate, it's going to be minus 1.97. That's the estimate for the beta 0. If I take the exponential of that, then you'll see that you reach the expected annual claim frequency of about 14% as it was calculated earlier on. Yeah, so this does the job. This does. Let me just go a little bit further and show you yet another way to calibrate the same model. And what we're going to do now is I call this the do-it-yourself approach. Yeah, because what we're going to do now is we're going to specify a function. We're going to write a function that evaluates the negative log likelihood in an unknown parameter for lambda, let's say. And what we're then going to do is we're going to use a numerical optimization routine in R, and we're going to ask R to do the optimization of this negative log likelihood for us. Yeah. And in a very general setting, you could do this as follows. So you're going to create a function which is called here neg log lik distr, so the negative log likelihood of your distribution. It's a function that is here going to use an unknown parameter denoted with par. This par can also be multidimensional, as you will see in the follow-up examples. We're going to rely on the frequency and we're going to rely on the exposure. So these are two entries, two arguments that we give to our function and which use the number of claims observed and the number of exposures registered, as they are available in our data set. And what you're going to do here is you're going to use a clever function in R, which is called D. D-dist is my general acronym over here. But the idea is, and you see that over here, that you're going to tailor that to the model that you're using with. For example, D Poisson refers to the density, or in this case, the probability function of the Poisson. So it evaluates the probability to observe a certain outcome frec, given that the mean of our Poisson should be modeled with a certain value lambda, right? And we can ask R to immediately calculate these probabilities at the logarithmic level. Yeah, so there is a built-in argument here, log is true. That means we're immediately going to take the logarithm of these probabilities. We're going to sum them all together and we're going to put a minus in front. And that's exactly our definition of the negative log likelihood. Yeah. So why do I do this? Log is true because numerically that turns out to be a bit more efficient if you use the built-in implementation within R. The alternative, of course, is that you take the logarithm yourself, but that's a little bit less efficient to do so. What we're then going to do is, for this function, we give it as input to a non-linear minimization routine called MLE. And we tell the routine, okay, you're going to minimize this function. Here, the parameter, the unknown parameter is one-dimensional in a Poisson model. So we give as a starting value just a 1. So that's just the starting value for the routine. We ask the routine also to calculate the Hessian. And that brings us to, at the latest classes that we've been doing, we know that with this Hessian, if we take the inverse of this, of the negative Hessian, then we know that we get the variance covariance matrix of our maximum likelihood estimate. So that will help us to calculate our standard errors that come with our estimated values, right? So we'll see that being demonstrated later on. For the frequency, I give the number of claims from the MTPL dataset. For the exposure, I give the exposure listed in the dataset. So if you tweak this general framework, let's say, to the Poisson, then you'll get an implementation like this. So what I'm doing here is, in the first line, I'm going to specify my lambda. And with my lambda, I have to be a little bit careful because I want to bring in my exposure measure there. So the lambda here is specified as the exposure times the exponential of the unknown parameter par that I want to estimate. So this par here is going to play the role of my intercept of my beta 0 earlier on. And the reason why I do that, positive, very good. So the lambda has to be positive. And a way to guarantee that it has to be positive is by putting this exponential function in here. Because then we can optimize the function over the unknown parameter par without bothering about any constraint optimization, right? If you would directly try to optimize the lambda, then you should work with a constraint optimization, because then you need to take into account that this lambda should always be positive. But by going through this clever transformation, we make sure that the lambda in the end takes a positive value. Okay, so what we're going to do then is we're programming the negative log likelihood of our Poisson model. We ask the routine to do the numerical optimization. We ask to calculate the Hessian, and we're going to inspect the results that we obtain as such. So let's do that together, and let's try to see whether we can reproduce the results that we obtained earlier on. Yeah. So earlier on, if you took the exposure into account, then the intercept that we calibrated was minus 1.97 with a standard error of 0.007. Okay. If we're now going to do that with our own written routine, we're going to look at a negative log likelihood of our Poisson. We're going to put everything into place, and we're going to do the numerical optimization with the built-in routine MLE. And we're going to store the results in sol poids. So if you ask to inspect these results, you'll get an output like this. So you get your minimum. So that's the minimum value that the numerical minimization routine reached. So that's my minimum value of the negative log likelihood. My estimate is minus 9.7. And my gradient is given like this. My Hessian is given. It's a 1-by-1 matrix because there is only one parameter. I get a code which is equal to 1 here. You can look that up by typing $MLM. So the output for the MLM routine is that you see something about a code here. If you go down. So when this code takes a value 1, it means that the current iterate is probably the solution. So it's a good sign. It means that our algorithm probably converged. Yeah. So that's what we have. So one of the things we immediately recognize is this estimate, the minus 1.97 value, which is the same as the value that we calculated earlier on with our GLM routine for the intercept, right? So we still need to take the exponential of that in order to figure out our value for the expected annual claim frequency. If we look at the corresponding standard error, what we then need to do is we need to take the inverse of our Hessian we need to take the diagonal element and take the square root of that. That will give us the standard error that comes with the estimate of my intercept, that comes with my estimate for the unknown parameter par. So in this case, if I do these manipulations, I get a standard error of 0.007. So again, if I look back to my earlier output, I recognize the same standard error. So this do-it-yourself routine is exactly doing what is in R happening under the hood if you run, for instance, this GLM routine. Now there is one question maybe that, and now I have to be careful how I explain it, but what we discussed in the class, if you look at our discussion of the Fisher information matrix, then we said, yeah, what you have to do to get the variance covariance matrix that comes with the maximum likelihood estimator is you need to take the inverse of the Fisher information matrix. But this Fisher information matrix is going to use the negative second order derivatives of my log likelihood, right? So here, the point that I want to make is when I calculate my Hessian, where did my minus sign go to? So for the variance covariance of my maximum likelihood estimator, we need to go with the inverse of the Fisher information matrix. And this Fisher information matrix contains minus the second order derivatives of my log likelihood. Now what the Hessian is doing, it's numerically evaluating the second order derivatives, right, of my log likelihood. So where did my minus go? The minus is somewhere over here, but where did I place it? So if I go one step back, of course, I've got this minus. Yeah, like Sebastian is saying, we're using the negative log likelihood. So that's where this minus sign that you may recall from the lectures, that is where this minus sign is going to. So it's perfectly fine to calculate the Hessian that corresponds to this function because it's already a negative log likelihood. So you can easily continue with that. And what we do here is we take the inverse of the Hessian and we take the square root of the elements on the diagonal. So that's the standard error that comes with our maximum likelihood estimate. And here it's the standard error that comes with our estimate for the intercept, for the beta 0 or for the expression of par, if you want. If you want to translate this standard error for the intercept to the standard error for the corresponding lambda, then you would have to go through the delta method. Yeah, so I didn't explain that on the sheets, but this is a case where you could apply the delta method to go from the standard error here at the level of par to the standard error at the level of the exponential of par. And that would require you to use this delta method. Okay. Any questions here? I think I'm going to stop here. I've got an additional example with the negative binomial, and then we're going to compare some model selection tools evaluated on our fits.